or your professor, whatever comes to you and say, I want you to measure chloramphenicol. So here's chloramphenicol, and it's an antibiotic, right? So, as a good student, right, you go to the web, start on the internet, and you get the structure of the compound that you're looking at. Excuse me. You get the structure of the compound you're looking at, and you get its formula. So you're starting to learn some things about the compound, right? And then you think, okay, well, I'm using a mass spectrometer. Maybe I should know the mass of the compound, what I'm looking for, right? So you go to the software, and I'll show you when we get to our software. And there's also a million different mass calculators available to you on the web. You type in the formula, and you start to see these different mass numbers that come out at you, right? So you have a nominal mass, you have an average mass, molecular weight, and then you have something called exact mass and something called monoisotopic mass. So in order to begin to interpret any high-resolution information, we have to know the difference between these masses, and we have to know the correct one to use. As you can see, there's a huge difference in these numbers. The nominal is 322, the average is 323, so that's almost one whole Dalton difference. And the monoisotopic has the decimal after it. The molecular weight is abbreviated to 0.2. So then to compound your work, when you do make the analysis of chloramphenicol, here's just a very short mass spectrum, and this is actually collected on a unit resolution instrument, but that doesn't matter for our purposes here. You see two peaks. You see a 320.9, so that would be like a 321, and you see a 322.8, that would be a 323. So why do you see two peaks? Why is there this mass difference, and why do you have these 5 different masses when you go to the calculator? So we have to understand all of this. So the first thing is chloramphenicol is analyzed in the negative ion mode. And in order to create a negative ion, we lose a proton. We're going to talk more about ionization today, so don't worry too much about that right now. But just remember, in negative mode, we lose a proton. So that's why here we have 321, and the nominal mass is 322. That -1 is the loss of the proton to create the ion from the neutral compound. And you may think, okay, well, we have another mass here. What is the 323, right? So for those of you who are familiar with isotopes, the chloramphenicol has chlorine in it. And we're going to talk a little bit about isotopes today. Chlorine has a very strong isotope pattern. There are 2 species of chlorine, and that contributes to having these 2 peaks in the mass spectrum. So when we have a compound that contains elements with an isotope, we're going to see more than 1 mass peak. And you may think, wow, geez, that's really complicated, right? But actually, we're going to use that to our advantage, because that will help us to identify compounds. So if you are looking for compounds with an element in them that has an isotope, you can then look for that distinctive pattern. You can see that. Okay, so a little bit more about these different masses. So these are the definitions of the masses that we had on the previous page. So nominal mass is easy, right? Nominal mass is the integer mass. That's just the rounding of the mass without the decimal. That's not so much use for us in high resolution, because we're going to use the decimal data from the instrument in order to help us identify compounds. Average mass is basically the same thing as molecular weight or molecular mass, and this is the average of the atomic masses of all of the elements. So what is that the average of, actually? the average of the atomic masses of all the elements. What does that mean? That means it takes into account the different isotopes. So if there is an isotope of the element, it will average that. An average mass, actually in mass spectrometry in general, should not be used. And that makes sense, right? We can see the isotopes. Let's go back to the data. Here's the data. You see the two peaks, or the two isotopes of chlorine, right there. So we wouldn't want to average those two, right? The average would be somewhere in the middle. And in the middle, we don't see any data. So you can see that the average is 323, right? It is in the middle of these two peaks. So the average or the molecular weight, don't really want to use that in mass spectrometry, because mass spectrometry we can actually see the isotopes. So that brings us to the last two definitions. The exact mass is calculated including the decimal. So we'll get to that in a second. Where does this decimal come from? So when we talk about exact mass, or some people will say accurate mass, we are using the exact mass of each element, including the decimal. And the monoisotopic mass is basically the same thing as the exact mass, but it is referring to the pure isotope peak. It is usually the lightest isotope, but not always. If another isotope would be higher intensity, it could be that one, but usually it's the lightest isotope. So the monoisotopic mass here would be this one here, right, 321, and that's why it says 322 here. Don't forget, there's a loss of a hydrogen because we're working in negative mode, so that's why there's a 1 Dalton difference. At least at the beginning, when you're getting used to the X500R and the data from it, you should always be using monoisotopic mass. And the reason is simple, because the mass spectrometer separates the isotopes, and it shows you the individual isotopes. All right, so let me ask a couple questions now to you. So, you know, when you buy a standard, for example, the triazines, and you look on the package, especially if it comes from Sigma Aldrich or something like that, do you know which of these masses it says on the package? Has anybody bought a standard in their work and looked on the package and looked to see what mass is there? No one? All right, so it usually says molecular weight, right? So be careful, especially if your compound has an isotope in it. If you buy a standard, usually the documentation and on the package it says the molecular weight. Can anybody guess the reason for that? What do you normally do? Let's say you have a powder and you buy ammonium acetate or you buy ammonium formate, right? Probably you used ammonium formate to prepare your solvents. And it says on the package molecular weight. What did you do with that powder? How did you prepare it? Is anyone there? What do you do when you buy a powder? You make a solution, right? How do you make a solution? You weigh the powder. And when you are weighing the powder on your balance in your lab, you are not separating the isotopes. So that's why it's important and why they write on the package the average mass or the molecular weight, because it's what you need to use in your calculations to make molarity or to make a solution. Whereas when we come to the mass spectrometer, we separate out those isotopes and we see them individually. And so then we need to convert to the monoisotopic mass to look at the data from the instrument. So nobody answered my questions. Is this clear to everybody? This is the number one point of interpreting high resolution data.
Yes, Alec, I think that's clear.
Clear to everyone? Okay. All right, so let's talk about the currency of mass. So the currency is the Dalton. And this ties into where this decimal comes from when we talk about the different elements and the different compounds. So we have the Dalton. You may see in older papers and so on, you may see that the Dalton is also defined as AMU, atomic mass unit. That is the same thing. They changed the name to Dalton, I don't know, like 30 years ago, 40 years ago, but still some people still say AMU. So if you hear people talking about Daltons or about AMUs, atomic mass units, it's the same thing. It's the currency of mass, molecular mass. So how do we define that? And this is very important, right? When you think about, for example, how we weigh ourselves, how we calculate our own mass in kilograms, right? How do you know if you weigh 50 kilograms or if you weigh 86 kilograms, how do you know what is a kilogram, right? So there is a reference somewhere in France. They have a kilogram and it's defined and that's 1 kilogram. And everybody knows that. And so they go back to that reference point, and that's why we can talk in kilograms. We know what that means because there's a reference. So we have the same thing in the mass spectrometer. It's called the Dalton. And the Dalton is defined as 1/12 the mass of carbon-12. So carbon-12 is the most abundant isotope of carbon on Earth. And the Dalton is exactly 1/12 the mass of carbon-12. So what does that do? That does a couple of interesting things. First of all, it means that the Dalton has a value of 1. Okay, that's obvious, right? 1 Dalton is 1. But the second thing that it does is it then makes carbon-12 have an exact mass of 12. So carbon-12 weighs 12.00000 Daltons, exactly 12 Daltons. There is no decimal. And the reason from that is our definition of what a Dalton is. Again, or atomic mass unit, if you're used to talking atomic mass units. Now, all the other elements and all the other isotopes, they have a decimal related to their definition of a Dalton, of how many Daltons they weigh. And that's very important. We're going to use this decimal in the interpretation of the data. So when you, we'll the slides every now and then. Okay. So when you look in the periodic table, here's the periodic table that you probably know it from high school and so on, right? Now, if you look, each atom, each element has its mass. And you see right away, well, there's a problem because carbon has a decimal now, right? So what's going on? I just told you carbon weighs 12. Because the periodic table doesn't separate the isotopes. So the average weight of carbon is 12.0107. But the exact mass of carbon-12, the monoisotopic mass is 12. And a little bit of carbon-13, the isotope, has a decimal associated with it. So be very careful, again, what masses you are looking at, especially when you're dealing with a periodic table like this one here, which doesn't actually define what is the mass that you're looking at. So I already mentioned about isotopes, so it's just text what I'm saying. And again, more text, the same thing. So what you actually need to look at is something called a table of the nucleotides. And what this shows you is not only each element, but also the isotope of each element. So on one direction of the chart, you have the number of protons. Right? The number of protons is what? That's what defines each element. So for example, here's carbon. Carbon has 6 protons. If for some reason we could change the number of protons, let's say we could do nuclear physics here for a second, okay? If we can change the number of protons, we change the chemical properties of that element, and it goes to a different element. So it is the number of neutrons that controls the isotope, or that is the isotope. Now, in the chart of the nucleotides, what we are primarily concentrating on are the black squares. The black squares are what we call the stable isotopes. And you can see here carbon-12 is 98.9%, and carbon-13, oh, my circle slipped a little bit. Carbon-13 is 1.1%. So what does that mean? That means every carbon atom that is in your compound has a 1.1% chance of being a C13. And then it's going to be a little bit more than 1 Dalton, not exactly 1 Dalton, a little bit more than 1 Dalton, mass difference. So this is a very important concept in high-resolution mass spectrometry, is to understand these isotopes, the stable ones in the black, and which elements have isotopes which contribute. So what I did is I made a slide here. This is a very important slide because these are the elements which contribute the most to the isotope. So for example, if we just go back, if we look at nitrogen, it's difficult to see it because my circle slipped, but nitrogen has an isotope, N15, that's stable, but it's only 0.3%. So that's a very tiny percentage. We're probably not going to see too much influence from nitrogen. Also, how many nitrogens do you have in your compound? Maybe you have 1, 2, 3 nitrogens, right? Probably not more than that. Whereas in your compounds, you're going to have a lot of carbons. Right? Carbon is primarily in the compounds we're looking at. And each one is 1%. So the carbon isotope will contribute strongly to your mass spectra. Now, so that's what this slide is showing. These are showing elements which have a strong isotope component. And there's only 4 of them, so it's easy to remember. And maybe really only 3. Boron is not so common, but it's fairly common. Carbon, of course, is hugely common, and chlorine and bromine are definitely present, in some medicines, drugs, in pesticides, and so on. So let's look at these percentages. As I already mentioned, carbon has 1% C13. Chlorine has 75% chlorine 35, and it has 25%, roughly 25% chlorine 37. So now if you think back to the mass spectrum we already looked at of chloramphenicol, that starts to make sense, right? We had 2 chlorines in that compound, and we saw that extra peak that was 2 Daltons difference. Where does that 2 Daltons difference come from? Because the isotope of chlorine that's stable is this chlorine 37. It's 2 Daltons from chlorine 35. Bromine has also an isotope. 79 is stable and 81 is stable, and they are roughly 50-50. Boron has B10 and B11, which are both stable, and it is in the proportions of 20 to 80%. So this is all important in identifying compounds with these elements present. So I think that's all I wanted to say about isotopes before we talk about isomers. Any questions here on isotopes?
If there's any questions, please, you can freely ask Mr. Alek Dooley. You can unmute yourself and ask him.
Yeah. Just call me Alek, no problem. And yes, please go ahead. Any question you are welcome to ask. Again, these are, you may think this is boring and you may think, what is this guy talking about? But if you understand these concepts, you will be able to interpret the data that's coming from the instrument so much easier. And I think this will help you hugely in your data analysis.
So I think that's clear for everyone.
Okay, great.
So we can continue.
Okay, so my slide is stuck again. Okay, so I just want to briefly mention what is an isomer. I'm sure some of you know this, maybe all of you know it, but the words are kind of similar. We have isotope and we have isomer. An isotope refers to a different species of that element that has a different number of neutrons. In an isotope, the mass is different, right? The neutron weighs approximately 1. So more neutrons or less neutrons means a mass change. An isomer is a compound, or let's say a group of compounds, that has exactly the same molecular formula. There is no difference in mass. So here I chose two compounds which perhaps we all enjoy at some point, these compounds. I think everyone understands mass, right? That's pretty easy. But the isotopes are maybe new to a lot of people, and this information is so rich. Look at this. We have, from this compound, we have 5 peaks here to look at, right? So we can use that information in the data analysis. So just to make it clear about this 1% thing, so here I have shown theophylline. So this is actually one of the isomers that we just talked about. Here's theophylline, and I have put a red dot on the 7 carbon atoms. So there are 7 carbons in this compound, right? The molecular formula here is C7. So it means there are 7 carbons. So those are the red dots. Each one of the red dots has a 1% chance to be a C13. And there can be a C13 at any of these red dot positions, and it will have the same mass as one C13 isotope. So that's important to mention. When the compound has all carbon 12s, each molecule that's present is the same, exactly the same, because they're all carbon 12s. But if we look at the peak that is 1 C13, it can be in one of 7 positions and still be the same mass, that same 1 C13 peak. And of course, when you go to 2 and to 3, then it becomes even more complicated. So there is a word for this, and this is combining the words of isotope and isomer. That's why I mentioned also isomers, and that's called an isotopomer. And these here, with these red dots on this page, they all have the same mass, but they represent, in a way, isomers of this one C13 isotope. So we call them isotopers. And this can also be important. I'm not sure if you will do anything like enzyme analysis where you are following a stably isotope tracer. So for example, you have a compound, you give it to an animal, and you want to see how it's metabolized, then you can look for the metabolites that are heavy with that stable isotope. But you have to understand that the isotope could be not just in one position in the molecule, it can be in every position where that element exists. In this case, there are 7 carbons. It can be in any of these 7 positions and still be that 1 C13. Any questions on this? All aced your physical chemistry courses. Okay, here we go. So 3 more slides, I think, on isomers, and then we'll move on. So I just want to emphasize that the isotope pattern will change with the mass. It's not actually changing with the mass, it's changing with the number of carbons. But as the number of carbons increases, that means the mass gets bigger, right? Then the isotope pattern will change. So here we see across the mass range from 1,000 up to almost 6,000, we see that the isotope pattern, or let's say the isotope distribution, changes as the number of carbons change. So here you can see at 1,295, so almost 1,300, still the all C12 is the tallest, the most intense, and 1 C13 and 2 C13s are less. And somewhere around mass 2,000, we finally have enough carbons in that compound that the chance of having 1 C13 is now greater than having none. all C12. So the density change there, you see that shift? And then as the mass continues to increase, we go up in the mass scale, we have more and more carbons, eventually here around 3,600 mass, so that many carbons. Now the peak with 2 C13s is the tallest. And 1 C13 is slightly less, and no C13s is down here now. Then, of course, as the mass increases, this goes up and up and up and up. So how do we know this? We know this because we know that chart of the nucleotides, right? We know the percentage of each isotope as well as its exact mass. So we can predict what the pattern will be like based on the formula of the compound. And you see this changing pattern as the number of elements changes. So actually, we will go, so just to go back to monoisotopic mass versus average mass. So this, we already talked about it a lot, right? That peak there is clearly the monoisotopic mass, this one here that's labeled. And just to overlay for you, here is a compound with the monoisotopic mass shown. So that would be this peak right here. And the average mass is right here. So the average mass is the average of all of these isotopes. So in the mass spectrometer, do we see anything at the average mass? No, right? It's the average. In the mass spectrometer, we see the real isotopes. We don't see the average of the isotopes. So this is, again, let's say a graphical representation of showing you why we should not use average mass or molecular weight in the instrument. And then I have the same slides again. So yeah, big red X, no average mass, right? That point is clear. And then this just says exactly what I said and why I asked you that question at the beginning. This is the answer, right? So when do you use average mass? When you are preparing something on your balance, because on your balance, you don't separate the isotopes. But in the mass spectrometer, we do separate the isotopes. So then we should use the monoisotopic mass. So I prepared a handy chart for you so you don't have to go and look actually all the time in a periodic table or in a chart of the nucleotides. Here is all the main elements that you have in your compounds. So we call this SNOPs, sometimes people say, right? CHNOPS are the main elements in biological compounds. And then I added here chlorine, bromine, and boron for you. I put the integer mass, I put the monoisotopic mass, and I gave you the isotope abundances, or let's say the most common isotopes, and then I put here also an average mass column. So this is kind of a handy chart that you can use for interpretation of your molecules. And of course, this is in the memory of the computer. So the computer knows this information. So when it's doing the data analysis in an automated way, it builds the mass and the isotope pattern from this chart. It's basically using this chart to do that. So if you put in a complex formula of, C12, H6, O3, and S, it builds that molecule from this data, and it comes up with the monoisotopic mass and the isotope abundance for that complex. All right, everyone okay with this?
Yes, Alek, all clear.
Yep, good. All right, how are we doing on time? So we've been about an hour. Okay, we're doing pretty good, I would say. All right, so let's say now we talked about kind of the basics of physical chemistry of what we are doing. Let's talk about how now we make the measurements. So this is now measuring mass. So there are two ways that are common in measuring mass. Parts per million is one of them, and you may hear people talking about that when they talk about ppm, right? Parts per million is ppm. That's probably the most common. And we also talk about millidaltons, m-daltons, right? Millidaltons. Observed would mean like experimental, right? And calculated would mean, for example, using this chart that we have here of what things should be. Or you may have, for example, a calibrant ion, and the calibrant ion in reference to another ion, something like that, the ppm difference between two ions that you have. So it's always between two things. And basically you take the difference, so you subtract those two and you divide it by one of them, and then you multiply by 1,000,000. Hang on just one second. Okay, just the construction was very loud for a second, I'm sorry. Okay, so we take the difference and we divide by one of them. Here it's the calculated, so observed minus calculated over calculated times 1,000,000. Now you can see these numbers are going to be very close to each other because we're multiplying by 1,000,000, and the best measurements on your system are going to be 2 ppm or better. So we have a spec on the X500R is 2 ppm or less. Now the interesting thing to note is parts per million adjusts with the mass because we're dividing by the mass. So 2 ppm means actually something very different at 100 Daltons than at 1,000 Daltons. So that is something to keep in mind. ppm number changes with the mass. Now millidaltons is easy. Millidaltons is just the position of the decimal. So this is the millidalton position, the 7, the decimal. Right, so that's 1,000 thousandths of a Dalton, and it just refers to how much you are off in that position. So you would just subtract the 2, and then in that position, basically subtract the 2 and divide by 1,000. Excuse me, and multiply by 1,000. So it doesn't adjust with mass; it's a fixed difference of the decimal. Unfortunately, millidalton is not used so much. Most, especially in organic chemistry. If any of you are building molecules in your lab and then finding that you've done the right reaction on the instrument with the product, all the organic chemistry journals basically require ppm mass measurements. So you don't see millidaltons really. We don't even have a spec in millidaltons. Also, our specs are all in ppm. But there it is for you to calculate both. All right, so let's take a look here at some of the differences or what the instrument can do in terms of mass measurement. So here I chose 2 groups of compounds to show you. The first one, they all have an integer mass of 150. Right? So here you see the formulas, and here you see the exact masses. The exact masses are different by the decimal. Now, why are they different? Because they have different formulas, right? And actually, you can see these two here, methamphetamine and phentermine, they have the same formula. By definition, they have the same mass, same formula, same mass, always. And so they would be isotopes of each other. We already talked about that. To calculate the ppm difference, we simply subtract these 2 numbers and then divide by one of them and multiply by 1,000,000. So you can see here, to tell the difference between cathinone, for example, and methamphetamine, which have the same integer mass but a different decimal, that would require 246 ppm mass accuracy. Now, 246 ppm is 100 times worse than what your instrument can do. Your instrument spec is 2 ppm. So this shows you really the power of this exact mass technology and the high resolution is that these 2 compounds with the same integer mass, we can easily tell them apart because they have different formulas. And we just have another example. I'm not going to go through the difference again for you. I think you can all read it. But here is 3 compounds. Again, 2 are isomers. They have the same formula. By definition, they have the same exact mass. And then the 7-aminoclonazepam is the same integer mass, but because it has a different formula, it has a slightly different decimal, and there's the mass difference required to tell them apart. So that's really the power of the instrument. We can tell these compounds apart simply by just measuring their mass very accurately. So we'll go through some examples now of let's say, the reverse. This is sometimes a little bit complicated for people, but the data can work in 2 ways, right? So yeah, actually, if I just go back and talk about this for a little bit more. So here we would be taking the formula and matching it to the data, right? So we have the formula, we want to search for cathinone, for example. We want to know, is there cathinone in the sample or is there methamphetamine? So we search for those two masses, and we can easily distinguish them, and then we could also get a ppm mass accuracy of how good the instrument is doing. So that would be, let's say, in that direction, you would be targeted, right? You know the compound, you know the formula, you're trying to say, is that mass present or not within the spec of the instrument, and could it be another compound, perhaps? But we can also go the opposite way, and this is perhaps the more interesting way for you guys working in more research-oriented work, is that you take the data from the instrument and you want to know what is the formula of that peak. So we would say that's the non-targeted way. Another way of thinking about that is formula finding. So we have the exact mass measurement from the instrument. Now we know how mass is calculated. We know the exact mass of all the elements, and we know also the isotope distribution. Can we take that data and fit a formula to it? So can we learn what is the compound without any prior knowledge? So that's what this example will go through. I'm cheating a little bit because I'm telling you, okay, that's the formula of what we injected C33H40N2O9 has a protonated mass of 609. So if we limit ourselves to the elements of C, carbon, H, hydrogen, and nitrogen, O, oxygen, we limit ourselves to those formulas, can we find out, if we limit ourselves to those elements, can we find out what is the formula of this data? See the data there on the right side. So if we had a mass accuracy of 165 ppm, then there would be 209 possible formulas using only these four elements that fit that data. And as you see, if you worked on more and more accurate mass measurement instruments, so if you go down to 2 ppm mass accuracy, then there are only 2 formulas that can match that information. So by taking the exact mass measurement of the compound, feeding it through the periodic table, and feeding it through the isotope calculator, we can come up with the correct formula from the data. In this case, we would have not one formula, we would have 2 formulas, and we would have to then continue perhaps with MSMS, which we'll talk about later today, to find out which one is correct. But we can do this by taking the data from the instrument and then finding out the formula. So we call this formula finding. So just to be honest, I don't like this example so much, so I prepared a second example. So here we have amphetamine, C9H13N. It has a protonated ion, so +1 proton at 136.11208, and I drew for you there the structure of amphetamine. So a 2 ppm mass range plus 2 ppm and minus 2 ppm is shown to you there, 136.11235 to 136.11181. There's a lot of small numbers in this one, right? So plus 2 ppm and minus 2 ppm, that's the mass range that your instrument could be within and the data still be considered good. So that is a difference of 0.00027 Daltons. Now, if we look at all of the formulas made up of CHNO with this error from the original mass that we got, 136.11208, there is then only one formula, which is amphetamine. So what does that mean? That means with your mass accuracy of your instrument, you measure a mass at 136.11208, you can exactly tell what is the formula of that ion. And once you know the formula, then you're well on your way to discovering what is the compound. So this is how we can identify compounds from the mass spectra itself using the high resolution. Now I have another example. I chose here cocaine. So it has the formula C17H21NO4. There's the protonated mass 304.15433. And I show you a picture of what the structure of cocaine is. So again, your instrument has the 2 ppm plus or minus 2 ppm mass accuracy. So you see the range there. That range is a 0.0006 Dalton range. Right, so I'm right here. Keep in mind the mass accuracy stayed the same, 2 ppm. But now we are working at mass 300. Before we were working at mass 136. Look at the actual difference. Here, the actual difference was quite a bit smaller than it is here. So mass accuracy measured in ppm does mean something quite different at different masses, as we already discussed. So again, there are, if we take the possible formulas made up of carbon, hydrogen, nitrogen, and oxygen with this error, we get 3. We get cocaine, and we get 2 other formulas. Now look at these formulas. 1 carbon, 12 hydrogens, and 20 nitrogens. It doesn't make sense, right? You can't put that together and follow normal organic chemistry rules. That molecule is nonsense. And the same thing here, C2, H18, N13O5, you couldn't draw a structure for that. So that's why it's written here, both are unreasonable compound formulas. And that's why it's important also to always consider the structure, right? The compound that you're building or you're finding from the data has to follow chemistry rules, right? You have to know that carbon binds 4 things. You have to know that nitrogen binds 3, that oxygen binds 2. And then you try to draw a structure with 1 carbon and 12 hydrogens and 20 nitrogens. It doesn't make sense. So you're using all of this information in order to interpret the data. Plus, you have also MSMS again, which we didn't talk about yet, but we will talk about soon. Okay, so that is the conclusion of the basics about mass, about isotopes. Okay, we'll continue. Okay, so mass analyzer scans. So remember, if you go back now to the picture of the instrument that we talked about at the very beginning, the flow path of the ions through the instrument, right, the schematic. Now we're going to talk about the analyzer region. The analyzer region is the region that does the filtration or the sorting by the mass. Now, in a QTOF instrument, QTOF means quadruple time of flight. In a QTOF instrument, there are only 2 scans that you can make. You can make an MS scan, which is what we're going to talk about here, or you can make an MSMS scan. Talk about MSMS second. These are the 2 scans the instrument can do. The instrument cannot do anything else. In that sense, this instrument is a very simple mass spectrometer. There's only 2 kinds of scans you can do. Now, when we actually get to the instrument and we start looking at the details, the scans are broken down into subsections, and there are some individual changes we can make. But on a conceptual level, there are 2 scans we can make. We can do an MS scan, which is looking for the intact compounds. Sometimes we call that a parent scan. Or we can look for an MSMS scan, and an MSMS scan in the instrument, we actually physically break the molecules and we look at those. We call them product ions because they are the products, or sometimes we call them the daughter ions. So we have parent ions in the MS scan and daughter ions in the MSMS scan. So here's a schematic of the instrument. All my schematics are always going to be the same. The ion path is always from left to right. And this 2 gold bars, that represents quadrupole 1. Here you have quadrupole 2, and here you have the time of flight. This is a little bit older presentation where we just had a U shape the V shape ion path, but the N shape is doing the same thing. The time of flight is working the same way, so don't let that confuse you. So how is this working? In this case, actually the quadrupoles up here in the front are just passing all the ions. So you see these big lines are drawn. These are the parent ions. They pass through the quadrupoles, and the time of flight does the separation. So what do we get from this data? We get a mass scan, and that is a mass spectrum, and that shows you all of the masses that were present at that time. And you, as the user, you can choose the mass range. So maybe you want to scan from 100 to 1,000, or I can't remember exactly from the email that you wrote, but I think you said 200 to 2,000 or something, right? So you choose the mass range based upon what's your idea of what's in your sample, and you get a mass spectrum then of what's present. Excuse me, hang on a second. All right, sorry. So this is also referred to as full scan. We are not focusing the instrument on any particular ion. We are doing full scan of the whole mass range. Whatever's present, we're going to see it. We're not tuning the instrument for one particular compound or one particular mass. We're seeing everything in that mass range. Now, this happens relatively quickly. You may get, 10,000 mass spectrum in a second, right? So it's almost too fast that we can't think about it. So we never look at the mass spectrum first. We always look at something called the chromatogram. Chromatogram is the collection of the mass spectra over time. So you can start to see here we have 3 dimensions of the data, right? We have the dimension of time. Time is ongoing. And for those of you who already worked with LC, you know that the time is mostly governed by the LC, right? You have your runtime. Okay, your experiment lasts 15 minutes. So you will be presented first with the chromatogram. And the other axis of the chromatogram will be the intensity. So here's our first chromatogram on the top. So here we have my mouse. Here we have intensity on the y-axis, and here we have time. So this is a chromatogram from an experiment done in a MS scan, what we just talked about in full scan. And you see all these different peaks coming out. Those are all the different compounds that have been measured. Now you can think about it as the third dimension is the mass, right? From the chromatogram itself, we don't have any mass information. We just see these peaks. So the mass spectrum is actually going back into the page. And you can see that when I have drawn that red line. The red line, if we look at that red line and we expand it out, then here is the mass spectrum at that time. So if I click on that peak, then I see, okay, there the main component is mass 582.78 at that time. And there are also some other masses. So we can see here, what did this person do? Maybe scan from 300 to 1300, right? So they scanned from 300 to 1300, and the chromatogram represents a whole collection of these mass spectrum that are collected over time. So we have to understand that it's very difficult for us to look at data in the third dimension, 3 dimensions. We can, computer screen is 1-dimensional. We think about things in, the computer screen is 2-dimensional. We think about things in 2 dimensions. So it's a lot easier to always see 2 dimensions, but you have to remember the third dimension is always there. So if we just look now, we can go back and forth between these dimensions. So the top one is we call it the TIC, total ion chromatogram. You'll hear that mentioned a lot. Look at the tick. Look at the tick. Total ion chromatogram. That is over time, right? Then we have the intensity. This is the sum of each mass spectrum that happened at each time point. Here's the mass spectrum. We already looked at it, right, on the previous slide. At that time, where that dotted line is, this is the mass spectrum. If we go to a different time, we're going to see a different mass spectrum. Different compounds come at different times. So what we can do now is we can do something called an XIC, and an XIC stands for selected ion chromatogram. X stands for selected ion chromatogram. And this represents just one mass over time. So here I can say, all right, this is all of the masses over time in this TIC. Now I've identified 582.78 as coming at that time. I want to see a chart of 582.78 over time. So I'm asking for a more simple chromatogram. That's what an XIC is, a selected ion chromatogram. It's selected for one particular mass. And you choose the mass, 528.78, and then you say, okay, where did that mass occur over time? So here we have time, and here we have intensity, but now we're not looking at all the ions, we're just looking at this one particular ion, 528, and you can see here it happens right at 20.21 minutes. So one of the key things in the interpretation of your data, there is, of course, automatic tools to help you, but especially if you're looking for unknowns, look at how busy that chromatogram is, right? There's many peaks here, right? If you want to look through that manually, you have to understand how the data is organized, that there is a mass spectrum going backwards into the screen at each one of these places, each one of these data points. You can look at that mass spectrum and you can create XICs. And of course, I'll show you how to do that in the software, and also SCIEX University has many courses in how to do this stuff in the software. But you have to understand what's going on in the data and how it's collected in order to look at this data. So the XIC is a type of chromatogram that is mass selective. So it does contain mass information. It's not shown to you exactly, but because you have chosen a mass range to show, it does contain mass information. It's also important to note, especially for those of you who have done MRM before, this is not generated by the instrument. This is generated from the full scan data during the data processing. So you are doing the data processing to produce the XIC. The instrument itself is generating the full scan across the whole mass range all the time. You are just looking at this one particular mass at this time. So that's how the data works. We're going to be looking at a lot of total ion chromatograms, a lot of mass spectra, a lot of selected ion chromatograms when we go into the data analysis. All right, so here is, this is basically a review of what we've already looked at. Here is a confirmation of a molecular formula from a mass information. So they injected a mass spectrum, and they got a formula from it with a mass error of 0.8 ppm. So they're able to confirm the presence of this compound in the sample using the parent ion scan. And that's what you can do. You can confirm or deny presence of formulas from the TOF MS data, from the MS data. So the other scan is a MSMS scan. In an MSMS scan, we take the compound and we actually physically break it in the instrument. So you can see here in Q1, we are, my mouse, here in Q1, we have quite some ions coming, different masses, but just one of them is selected. One mass is selected. So we're using the Q1 to filter one parent mass. That parent mass enters into the Q2, and the Q2 is actually a fragmentation chamber. We physically break the parent into daughter ions. You can see it's breaking into different daughter ions. And then in the time of flight, we make the accurate mass measurement now of those daughter ions. So MSMS just means we're selecting a parent, we're breaking it in the instrument, and we're looking to see what are those daughter ions. What are the pieces of the main parent. This is what the MSMS data looks like. Actually, it's presented to you here as part of a whole experiment. So we see already the XIC on the left side. This is the data that we just talked about from the MS scan. Here is the MS scan in the middle. So do you see the red line? There's a red line here. That red line is the time point where the mass spectrum is taken from. The blue is the mass spectrum of the data, And underneath it, you have the isotope pattern of the calculated formula which this matches to. And then here on the right side is the new information. This is the MSMS. All of these ions here, our library is a collection of MSMS scans of known compounds. And that's stored in the database. We call it a library. And so we can do something with MSMS data called library matching. That's one of the main functions of why we want to do, or why we want to collect MSMS information, is in order to search it against the library. See down below, it's just another example. Different compound, different XIC, different mass spectrum. Here's 233 as the parent, and then here's 233, and then these are all the daughter ions of that parent, and the library match is shown underneath. So together, MS for the formula and MSMS for the structure, these two informations come together to help us to identify the compound. And we are going to talk about MS and MSMS in a lot more detail. That was just the introduction. So any questions? All right. So now we will talk more about the hardware. The first point is the solvents. I cannot stress enough to you on how clean the solvents need to be. On this instrument, it is required that the solvents that you use are LCMS grade. And we kind of already understand why, right? This is a full scan instrument. Full scan instrument means it is detecting everything in a mass range. Everything. It's not targeted on one thing or something. It's detecting everything in the mass range. If your solvent is dirty or contaminated, then those will show up as ions in your mass range and will complicate immensely your task in the data analysis. So for that reason, and also for the cleanliness of the instrument itself, so the instrument does not get dirty, as I mentioned in the interface region, we do have to clean every now and then. Everything should be LCMS grade. So please do not use anything that is less than LCMS grade on the instrument. Now this slide contains my recommendations to you. If you, especially at the beginning, if you use only these solvents, you will be 100% okay. This is like the good list, right, of the solvents. So you should use mixtures of water with methanol and or acetonitrile. So those are your three solvents that make up the bulk of the liquid of the mobile phase. Water, the A solvent, and some organic methanol and or acetonitrile, either a mix or separately, is in the B. Now you will need to add some buffer. We didn't talk about ionization yet, and we'll talk about that. The buffer has two purposes. One is to help in the ionization, to control the pH and to either promote protonation or deprotonation, depending on the pH. And the other is to work as a counterion in the chromatography to improve the peak shape on the LC. So in most cases, you will use a buffer. There are a few cases where maybe buffer is not applicable. Those are pretty rare. So we need to add a volatile buffer. So don't forget, the second job of the ion source is evaporation. Right? We said it has two jobs. We said it of course creates the ions, and the second job is to evaporate the liquid of the LC. So normally we use a volatile buffer such as ammonium formate. Actually, ammonium formate would be my #1 choice, or ammonium acetate. And those also must be LCMS grade. Ammonium acetate and ammonium formate are hygroscopic substances. Hygroscopic means that they absorb water very readily. Unfortunately, they don't absorb water, they absorb it as moisture from the air. when the bottle is opened and so on. And this causes them to become dirty very quickly. So I highly recommend, also because it's expensive, that you buy ammonium acetate and ammonium formate and you buy it in a small size, 50 grams. Don't buy more than 50 grams. And it's basically expired after 2 or 3 months. So it doesn't make sense to buy something like a kilogram because it'll go bad before you can. So again, this is all readily available from many different suppliers that sell ammonium acetate or ammonium formate in LCMS grade. We can also add an acid in positive mode, for example, formic acid or acetic acid. My choice would be formic acid. 0.1 to 1% to support the protonation. Again, the formic acid is hygroscopic, it goes bad quickly. The expiration is roughly about 2 or 3 months, and you need to buy LCMS grade formic acid. Negative mode, conversely, we can add a base to support deprotonation, and that would be ammonia. Now, ammonia is a gas, right? So you buy this as a ammonia dissolved solution, and I think you can buy something like 27% or 28%. They sell it for LCMS, and then you dilute it down to 0.1%. So most common would be ammonium formate at 2 millimolar and formic acid at 0.1%. If you use that, that's a very good start. Personally, when I'm starting an analysis and I don't know too much about what I'm doing, I start with that. I'll make ammonium formate 2 millimolar and formic acid 0.1%. So again, everything on this page is required to be LCMS grade. All of the solvents here are volatile. They all evaporate readily in the ion source, and they do not leave any residue behind. Now, I get a lot of questions about the samples, so I put this in, actually, this is a new slide for today. This doesn't mean that you can't inject dirty samples. So what we are talking about here are the solvents, which are the running solvents. These are the mobile phase that are continuously pumped through the LC and continuously fed into the ion source. That needs to be as clean as it possibly can. Of course, the purpose of the LCMS is to analyze dirty samples. If you think about it, your sample will be injected onto the LC in a very small volume. Maybe you will inject 5 microliters or maybe maximum 10 microliters or something. And the purpose of the chromatography system is to separate your compounds from the matrix, which is the dirt, the salt, and everything else in your sample. So don't get confused that your samples need to be prepared with LCMS grade solvents. That's not true. Your samples are, of course, dirty. Dirty is, of course, a relative term, right? They are like a plant extract or a bacteria extract or something. And we are just injecting a small amount of them into the continuously running mobile phase, and that continuously running mobile phase must be LCMS grade. So please follow this. This protects you. It makes your data analysis factors, or let's say orders of magnitude, easier, and it protects your investment in the instrument. All right. So here is an example of why we are using the modifier for the ionization. So this is a 4 mass spectra of progesterone. Now, progesterone has molecular weight 314. So we see it in the positive mode at 315, right? Because we're adding a proton. The top mass spectrum is in water acetonitrile. And then as you go down, you see that the concentration of the ammonium acetate is increased. 2 millimolar, 20 millimolar, 100 millimolar ammonium acetate. Now, they look roughly the same until you look at the y-axis. If you look at the y-axis and you look at the intensity, you can see that there's roughly 2 times or more than 2 times, almost 3 times increase in sensitivity when you just go to 2 millimolar ammonium acetate. And then as you increase the ammonium acetate further, 20 millimolar, 100 millimolar, actually the intensity goes down at 1.7 E6 and then 1 E6. And that goes along with what I'm saying about being clean, right? Just 100 millimolar ammonium acetate basically gives you half the signal what you had without it. So why is that? It's because the ammonium acetate is now so strong, it's acting like a dirt. And it's stealing all of the ionization power and the ion transmission efficiency of the instrument. And that's not a very strong solution, 100 millimolar. It is in terms of mass spectrometry, but in terms of contamination, it's not very strong. So this slide shows you not only the importance of using the buffer at the right concentration to improve the intensity, but it also shows you what can go wrong if you have contaminated solvent. So what are some troublemakers? So like I said, if you stay with the components that we had on that first slide about solvent, you will be 100% okay. I guarantee you that. If you want to use something else, especially at the beginning, you're welcome to write me a short email and say, hey, I have this buffer system from this paper. Can I use it? I will answer you. Some things that are definitely no-nos for LCMS. So anything that is a non-volatile salt. So for example, sodium phosphate, sodium chloride, etc., cannot be used in LCMS. And the reason for that is they're not volatile. So when the liquid evaporates at the ion source, these compounds will be left behind and they will just really gum up your source. There will be all crystals of salt throughout your source. So please don't use these kind of non-volatile salts. Again, this is in the mobile phase, not in the sample, right? The mobile phase. Any kind of inorganic acid, hydrochloric acid, sulfuric acid, etc., should not be in the mobile phase. That'll just eat the metal parts. So there are some chromatography systems that use that, but generally they are inert. We don't have an inert system here, so don't use inorganic acids. Other popular modifiers, especially if you were looking at an older paper or an older method, let's say from 15 years ago and before, those are TFA and TEA, trifluoroacetic acid and triethylamine. In those days, the mass spectrometers were not so sensitive. Now we have much, much more sensitive mass spectrometer, and these compounds, it turns out, leave a trace in the opposite mode. So trifluoroacetic acid, so it's an acid, so you would use it in positive mode to promote proteinization, but then if you change your instrument to negative mode and you do some work in negative mode, you will see the TFA at mass 113. And conversely for TEA, you'll use, it's kind of basic, so you'll use it in negative mode, then you switch to positive mode, you'll see the 102 in the positive mode. Don't use, in the modern instruments, TFA or TEA. In many cases, you can convert. So TFA, you can use formic acid, and the TEA, you can use ammonium formate. It's not, of course, perfect one-to-one, but in many cases, it will work. So that's not what to use. So we'll just go through a couple horror stories here. Hopefully scare you a little bit. So here we have effect of a phosphate buffer. So this person used phosphate buffer, and you can see this is a mass spectrum, not a chromatogram, right? So that's a mass spectrum on the top, and you see all of these masses just everywhere. So what are those? Those are actually then the clusters of the phosphate salts. And can you see your sample? Can you see, or sorry, not your sample. Can you see your compound there? No, it's very hard to know what's your compound, what's the background, right? It's just a mess. And then the phosphate buffer has been removed. And in this case, I think CCK is some peptide, small peptide, couple amino acids. There you see clearly when you run in formic acid, you see the clear peptide. So that is an example of, please don't use phosphate buffer. And here's another example of contaminated solvent. So this goes back to the triazine analysis. So this is a full scan instrument. Now the top pane is the mass spectrum of the triazine mix. For those of you who worked with Mare, you know the masses. I know them because I use triazines a lot, right? So here's 202, 216, 226, 228, 230, and 242. Those are the 7 triazines. So that looks very nice. You have a good signal, and notice that your signal is somewhere in the E6, half E5 to E6, so that's a very good signal, and the background is quite low. Now, let's say you're looking at the same compounds, but you have it in contaminated solvent. Let's say you don't know. So you scan the same range, and you're looking for those masses because you know the triazines, and you don't see them. Okay, maybe we can kind of see here a little bit of 226 and 228, right? Maybe that's a little bit distinctive to you. That's really hard to say, right? 242 is there, but what's 233 and so on? So unfortunately, if you come to this point, what is your assumption? Most people here, they make the assumption that the concentration of their compounds is too low, right? Unfortunately, that's too self-centered. You have to look at the instrument as well. So the problem here is not the concentration of the analytes. The problem is that the solvent is contaminated. Now, it's kind of difficult to tell at this point because the mass range is a little bit narrow. So what I suggest you do if you have this problem is that you then open up your mass range. So here is now a scan from 50 to 500. And look at what we see. We see all of these peaks. What are all of these peaks, right? This is some contamination in your solvent. Now, if you look a little bit closer, you can see that they are equal distance apart. So we have here, right, this one to here, here. It's like a ladder. See that? They're equal distance. And I think if we pulled out a calculator and we did the mass difference, we'd see that it's the same subunit. So what is that? That is a polymer. We see masses like that of all the same difference throughout the mass range. That is a polymer that has gotten into your solvent. And polymer is the #1 contamination because unfortunately polymers are everywhere. Right? They are the main components in soaps. They are the main components in plastics. So if you do see any kind of pattern like that one that we're looking at there, or let's say a very high ions, your solvent is unfortunately contaminated. And the easiest thing to do there is to start from the beginning. The #1 source of contamination is the buffer. Like I said, the buffers are hygroscopic. They will suck contamination from the air. So if you do see contaminated solvent, I strongly suggest you go back to your stock bottle. If the stock bottle has been open more than 2 months, you set it aside and you take a new stock bottle and you prepare all fresh solvent. Now you can, of course, try to isolate where it's coming from by trying different things and so on. You're welcome to do that. But in this case, as you can see, you can't see your compounds. It's not because of the concentration of the compounds, it's because of all of this other junk or polymer, which has somehow made it into your solvent. So that's why we spend so much time on solvent and why I stress always to be at the cleanest level possible. So here is an example actually from an X500R. So I don't know if you saw, but these examples are all from a triple quad. So this example here on this page now is from the X500R. This is an example of a good solvent and contaminated solvent. Now you might think, what on earth is he talking about? Because the good solvent has a lot of peaks in it. You can see some peaks there. But take a look at the y-axis. The y-axis of the good solvent is 1500. And the y-axis of the contaminated solvent is 9E4, right? 90,000. So we're way more than 10 times. Let's say, yeah, almost 50 times, right? Higher. So LCMS is never clean. It's a dirty technique anyway, and you see that as evidence of what are all those peaks in my good solvent, right? There's always some peaks, but that is an acceptable level of what is considered a good solvent. And contaminated solvent then would be shown as below. You know, once you start getting into the high E3s and E4s, for sure, that's contaminated. And I'll show you how to check this when we go to the instrument. You can check this from each of your runs on a daily basis, and you can see immediately if someone's solvent is contaminated or not. Okay, so any questions on solvent? Does everybody understand the difference between what is acceptable in the mobile phase and what is acceptable in the sample? That is a key difference.
Everything is clear.
Everything is clear. Excellent. Okay, what I suggest here is we just take a 5 minutes break, bio break. I need to refill my water glass. So we'll take a 5 minute break. So right now it's 3:15, so we'll join again at 3:20, okay? I'll see you guys in just 5 minutes at 3:20.
All right, thank you, Alek.
باله طويل هلكني قمت صليت
بلشت تنطي في باكت القهوة يعني.
هو لازم يكون هيك.
ايه بيعتبر انه العالم ما فاهمين شيء.
لازم يكون هيك لانه
بيعتبروا
انا بس تتعقد الوسط لانه لسه اذا ما كانوا فاهمين ولا انه في ايسوس حيطلع معك قدام منطق حبيبي اذا تفهم انا بعرف عليك انت معصب بحكي لها
كنت عم بعمل قهوة شوي حطيتها ومدري كيف زحت الدنيا طفشت الدنيا وبلشت تقضي
لا يا حبيبي انا بشوف
انا باول ما فتت اي جوي كنت وعم بفكر فيديو فاتح الكاميرا بعد طفيت اشتقت الزكاة لما الزكاة كل مرة شيء بكرة حتقولي لهم يجوا يحطوا
انا حكيتهم من قبل اول سنه اول سنه
ولا تورس عندنا
bankers.
bankers
Bankers.
little file
طبعا بنتي شو $800 يمكن اول ما بلشت هيك بوقت هلا بعد انا بنسى
بعطيه اول السنه
ايه بالجانيوري
بلبنان
ايه دخلت على 2005 كمان كان اوريدي طالع كان
كملت
دبل يعني وبعدين هلا اشوف
رجعت
هلا
عندي.
كده يمكن اقول لهم بقى بدي سياره يعني كان
انا
وقفت
السنه الماضيه وقفت كنت عامل تورست للسيارتين وقفت قلت لهم بس الزين وضد الغير يعني يطلعوا 1005 اثنيناتهم
اذا بدي يقولوا لي بالدولار وبدي
All right, guys, so I'm back. Get some more water. All right, so we will continue. Yes, we will continue. What time is it? Yeah, obviously 3:20. Okay, so we'll continue for another little bit over an hour. Okay, so the hardware now we'll go through. Just take a look at the instruments. You guys can see what it looks like. Probably you've all been in the lab and seen it anyway, I guess. So this is the X500R in the center. So that's the QTOF. You have the big tube going up. That's got the time of flight in it, time of flight chamber. Couple points that we'll go through. So this is the ion source on the front. And you would have the connection from the LC right here. A silver piece. This is called the grounding T, and that prevents any electricity from the ion source leaking back to the LC. Over here on the left, you have the LC. This is an Xion AC system. I guess this is probably what you have in your lab, although I'm not 100% sure what LC you have. So you have here pumps, and this is the auto sampler, and this is the column oven, and then the exit from the column will go through red peak tubing up here to the grounding T, up to the source, and then down inside the instrument. The evaporation and the production of ions will happen in this little chamber right here. And then basically the flow of the ions goes back through the instrument. Of course, inside, we can't see it in this picture inside, and then up in the time of flight. The software we're going to use is called SCIEX OS. I think you guys all know a little bit about that already because you worked in the SCIEX University and so on. So that's great. That'll give us a head start when we start in the software tomorrow. All right, so it's a small footprint and so on. These are a little bit more marketing slides. Okay, so this is important. These last 2 points are important for training. The instrument has integrated calibration. Now, time of flight is, or let's say, needs to be calibrated often. We recommend that it's calibrated once per hour. Batches, and I'll show you how to set that up. It is all automatic. And the solution is injected from these bottles here on the front of the instrument. You have 2 bottles, which is handy, one for positive mode, one for negative mode. A little bit of that solution will be taken every hour and injected into the ion source. The instrument will be automatically calibrated, and then the instrument will continue with your analysis. And if you do that on a once per hour basis during your batch runs, then you will maintain this 2 ppm mass accuracy, which we just spent so long talking about. So that is then linked to why we have a twin spray and why the source is called a twin spray. The twin spray source has 2 channels in the source. I'll have a closer slide in a few slides. And one of those channels is for the calibrant, and one of them is for the LC. So you will see actually coming out of the instrument another line that goes up to the source. So you have 2 tube connections to the top of the source there. This is already the ion path, which we already talked about. So you have here the Q1. This part is all referred to as the interface, the QJ, the Q0. You have here the collision cell, so that's where we do MSMS. We're doing MSMS. Then you have some ion transfer optics and an accelerator. You have the time of flight path up to the first reflector, down to the second reflector, and then up again to the detector. Okay. Okay, so that's kind of the overview of the hardware. Now we will go step by step through each piece. So the ion source is first. So for those of you who have used our other systems, this is still referred to as the Turbo V source, and we'll talk about why it's called the Turbo V source in the next slide. But that even though it has a different cover, and it's gray and blue, and it matches this instrument, it still has all the same principles that a normal Turbo V source will have. So this is the source, let's say, removed from the instrument and turned 180 degrees. So you're actually looking into the part of the source which would be attached to the instrument. So this black ring here, that makes a seal with the instrument itself. So here's the connections for the LC and the calibrant up here at the top. You have some adjustments for the position of the source, a vertical one which is behind and a lateral one here. To be honest, I don't play really too much with the source position. You sometimes read it a lot that people tune the source position and so on. I would say, for general work, a wide detection of a wide amount of compounds, we'll just leave the source right in the center. Now, how does the source actually work? So there's a very thin capillary down the center here. Then we have a spray that comes out of this tip here. So it's invisible, but there will be a spray coming down there, very similar to like a hairspray or a spray paint, very fine spray of droplets, and that is the liquid from the LC. Now on either side you have these two heaters. You can see it's kind of this blue-gray color. One is here and one is here. And that's why it's called the Turbo V source. So these two heaters, so here you have the LC flow through the capillary. And then you have this capillary is sitting inside another capillary, or a slightly bigger tube. And between the two, you have what is called gas 1. Gas 1 is basically compressed air coming from the gas generator. And those flow of gas and solvent together create this fine spray of droplets. Again, like an aerosol, like I said, a can of spray paint or hairspray. And so you have this high, or let's say very wide, very fine spray of droplets. Now, at the same time, this needle is made of metal, and there is a ion spray voltage applied to that needle. And here we are talking about thousands of volts, maybe 4,000 or 5,000 volts. And so that charge is transferred to the droplet. Here you see the droplet. This is a droplet of solvent. Inside it, you have all of your compounds. You also have everything else that's present at that time. And now it's covered in charge. You see all these little positives are covered in charge coming from the ion spray voltage. Now these are the two heaters, and the heaters have the settings gas 2 and heat temperature. These heaters are just working like little hair dryers. Right? When you have your hair dryer, what's happening in the hair dryer? The hair dryer has two components, right? It has a blower and it has a heater. And they work together to create the hot airflow that dries your hair. Here we have the same concept. We have gas 2, which is the blower, the flow of gas, and we have the heat, which is the temperature. So together they are working to create a flow of hot air in the direction of this orange arrow. And that, like I said before, that's pointed right at the spray. So what happens in the spray is evaporation. And you can see the droplet is getting smaller. The charged droplet gets smaller, solvent molecules leave. They go to the gas phase. So what happens to the droplet? The droplet is smaller, it has the same charge. Right? We didn't lose any charge, the charge didn't go anywhere. So the charge is still there, now on a much smaller droplet. So the charge starts to affect the compounds inside it, and as this evaporation continues, eventually the droplet gets so small that we have what's called a Coulomb explosion, a charge explosion. And the droplet basically, poof, explodes, and it may go through several steps of explosion as it gets smaller and smaller. or maybe just one. And what is ejected from the droplet is our molecule now as an ion with a hydrogen attached, positive mode. Negative mode, of course, everything will be flipped and it will be ejected without a hydrogen minus. So that's the ion of interest. And this is how we create what's called a gas phase ion. Right? We need the ions at the gas phase in order to get them into the instrument and to be able to manipulate them in the vacuum. We need to get rid of the solvent, and we need the ions. So we have two things here in the source, the creation of the gas phase ion. And now the gas phase ion can enter into. So that's how the ionization is working. Now here it's steps 1, 2, 3, 4. That's just to explain to you how it's working. This is a continuous process, a continuum. So there's more solvent entering, there's more droplets behind, the droplets are evaporating, the charges are, charge explosion is happening, the ions are ejected. This is a continuous process, a smooth, continuous process. Just like when you turn on the hose pipe, put your finger over the end of it and you water your garden or you spray down your driveway or whatever you do with your hose, right? That's a continuous flow of water, continuously happening. The same thing here. This is a continuous flow of ions. We sometimes call it an ion beam, like a laser beam. It's a beam of ions created by the source in the gas phase, which is then continuously entering into the instrument. So we have a continuum, and if we connect this up to a chromatography system, it's perfect, right? So the LC is pumping, peaks are coming and going, and this process is a continuum, constantly producing the ions that are fed into it from the chromatography system. So this is a really powerful technique. It ionizes many kinds of molecules. And it is really great for biological molecules, which I think the reason you purchase the instrument in a very wide scope is to analyze biological molecules. So again, why do we need ions? We need ions because in the analyzer, we're going to set up magnetic and electrical fields to sort and to filter by mass. So a neutral compound will not respond to those electric and magnetic fields. So those are called neutrals, and we can't analyze those. So mass spectrometers only work with charged molecules, ions. And I already mentioned this, they can be positively or negatively charged. Positive charge, gain a proton, negative charge, lose a proton. And since hydrogen weighs approximately 1, as we know, not exactly 1, when we talked about mass earlier, but approximately 1, they will have a different mass than the neutral. So either +1 positive or -1 negative. So we'll just go through a couple examples of ionization. And this is important because you're going to need to factor this in when you are doing your compound identification. So an ion is a charged form of the compound and comes from adding or subtracting the proton. So let's just look at this compound. So here we have the neutral M, and there we have a nitrogen. So what's important about a nitrogen? Why is the nitrogen singled out? The nitrogen has what's called a lone pair electron. So from our organic chemistry binding rules, nitrogen likes to connect up to 3 other elements, right? 3 other atoms. But it has this lone pair electrons, which occasionally will attract another hydrogen. When it does that, it takes on a positive charge. So here you see the positive charge almost certainly occurs at the nitrogen. And that generates the positive ion, which is referred to as MH+. So M stands for mass. So you have neutral is just M, and you have your positive is MH+. Now, in the negative mode, and it's important to note that this is not happening together. This is just 2 examples. In the negative mode, the opposite needs to happen. But there is something important important about the compound work in negative mode. In negative mode, the proton is lost. What does that mean about the compound? It means that it has to have a proton to lose. So if you have a compound that doesn't have a proton that's easily lost, you will not see a signal in negative mode. And for this reason, less compounds are analyzed in negative mode than in positive mode. A lot of biological compounds have nitrogen, therefore they work well in positive mode. Not so many compounds have a hydrogen that is freely, easily able to be lost. So here we have a carboxyl group, and the carboxyl group is here, right? So this is COOH. And what happens is then under basic conditions, this hydrogen will leave, and this oxygen is okay with a negative charge. It hangs out here, and so you have the negative M minus H minus. So in terms of percentage, I would say about 85% of compounds is positive mode, and about 15% work in the negative mode. So the key point for negative mode is they must have a proton that can be lost. So if you don't have any carboxyl groups and you don't have any OH groups, you're not going to have a proton that can be lost. So it won't work in negative mode. So this is not dependent on the instrument. This is dependent on the compound, right? This is a property of the compound, whether it's going to work in positive mode or negative mode. So here is just a little short thing on how to calculate mass. So primarily, we bought the instrument for small molecule work, and I also work in small molecules, so I also do the same thing. I talk only about mass. But just remember the instrument is measuring mass to charge. However, when your charge is 1, you're dividing by 1, so you end up with the same number. So you just have to be aware of adding or losing a proton. However, higher molecular masses, let's say above 1,000, especially proteins and peptides, if you do get into that kind of work, you may see doubly charged or triply charged or higher, and then the ion will show up in the mass spectrum as the mass to charge ratio. So if you have something that is mass 1500, that's 1500, and it has 3 protons on it, then it will be 1503 mass, because you added 3 protons, divide by 3. So you will see it at 501 mass to charge in the instrument. So that's basically what this slide is telling you. Be aware of the proton, the gain or the loss. That's the M up above, and then make sure you divide by the charge. The nice thing is the number of protons added or removed is the charge, right? So you don't have to do any further calculations. If you add 2 hydrogens, that's a +2 charge. So here, calculating the mass per charge of tryptophan. So this is the same molecule we already looked at. All right, so it's 204. So we add a proton. So the charge is 1. So it's M plus number of charges times hydrogen divide by number of charges. So it becomes 204 plus 1 is 205 divided by 1. And opposite for the negative, N is 1. But we lost 1 hydrogen, so it's M minus NH over N is 204 minus 1203 divided by 1. So that's how we go back and forth between mass per charge and mass. Like I said, I think primarily your work is going to be small molecules below 1,000, so you will not have to worry so much about charge state. Okay, so this is kind of a guide of how you can choose positive and negative, right? I think it was clear from the example there we just went through that if you have a nitrogen in your compound, you're going to work in positive polarity. That's kind of the nitrogen rule. If you see a nitrogen in your compound, go with positive mode. Other examples of compounds that work with positive mode are ethers or esters, and if you have an ether or an ester, that may be an example of something where you may form an adduct, which we'll talk about here in a second. A thiol is a sulfur group, so if you have a sulfur compound, or if you have a sulfur atom in your compound, it's also a candidate for positive polarity. Negative polarity, again, you have to have the hydrogen to lose it. So it has to have a carboxylic acid or a phenol that will be lost, or actually something with a phosphate group in it also works great in negative polarity. So what is an adduct? Well, actually, an adduct is anything that is sort of joined together, let's say, almost ionically. So the M plus H is called a quasi-molecular ion. Even though we say it's the parent mass, technically it's not exactly correct, right? Because it has the hydrogen is the adduct. So we say it's a protonated quasi-molecular ion, MH+. Now you can also get true adducts, I would say, with other charging species if they are present. So alkali metals, such as sodium and potassium, right? They are in the same, same period in the periodic table, right? They can also form adducts, and then instead of the hydrogen, you have the sodium or the potassium atom. Keep in mind that drastically changes the mass. Okay? And then you have also the possibility of an ammonium adduct. From the previous slide, you saw it said ethers and esters. If you have an ether or an ester, that's a prime candidate to form an ammonium ion, M plus H plus. Negative mode is the same thing. You have this deprotonated quasi-molecular ion, M minus H minus. And then adducts can form in negative mode, which is a little bit strange because you're adding something that brings the negative charge. So you have M plus formic acid and M plus acetic acid, and then the acid adds the carboxyl group, which has the charge. So if we look at the mass spectrum there, you can see your M plus H is at 1013 marked. And this is really, this is really a little bit of a crazy example. You do not usually see 5 ions like this for one compound. Usually you see maybe 1 or maybe 2. For example, you may not see the M plus H, you may see only the M plus sodium or M plus ammonia. But it's all laid out there for you. Now keep in mind, the mass difference that's indicated, the plus 17, is already from the 1, right? So this is 1013.6, this is M plus H. So from the neutral M, NH4 is 18, right? Nitrogen is 14 and 4 hydrogens is 18, not 17, because this is the addition from the 1 hydrogen that's already here. So you have to take 1014 and minus 1 plus 18 to get the plus 17. So this slide with these numbers here as a function of a difference from this mass is a little bit confusing. Just bear that in mind that the 1013.6 already has 1 hydrogen added. So there you have the ammonium, which will be a 17 in the mass spectrum or an 18 in neutral. Sodium is 23 in neutral, right? But 22 difference in the mass spectrum. Potassium is 39, but 38 in the mass spectrum. And there you have a minus 18, which corresponds to a water loss. So that is an M plus H and then minus a water. And that's also a common thing that you may see is a water loss from some compounds. Again, they have to have, if you lose something, you have to have it to lose. So if you don't have a carboxyl group or some OH across a double bond, something like that, you're not going to lose water. So just bear this in mind. If you don't see your target compound on your first look, you may need to look also for these adducts. This picture here is not a good representation that you can see all 5 ions. You see only 1 or 2. So you may not see the MH plus, and you may have to go and look for the ammonium. So here we have the adducts and the mass shift. Now this is where it's confusing, right? That's the mass shift from the neutral. So in the previous slide, the spectrum was marked as the mass shift from the +1 charge. You have the polarity that they work in, you have the exact mass shift, and you have a source where they could possibly come from. Now, sodium and potassium primarily come from glassware. They may also come from the matrix of your sample. The nice thing about sodium and potassium is that you can usually convert them to ammonia adducts because the ammonia source is the eluent primarily, right? We're adding ammonium formate, we're adding ammonium acetate. So if you are using ammonium-containing buffers, your primary adduct will be ammonium, the M+H, not potassium or sodium. So that's something to keep in mind, and maybe an advantage of why you would want to use ammonium formate in your buffer. Okay, so these are the source tuning parameters. Now the source, we call it flow rate dependent. Flow rate dependent. What flow are we talking about? We're talking about the LC flow. So the source parameters are primarily going to be tuned depending upon what flow rate you put into the ion source. So if you put high flow into the ion source, then you're going to need to increase your source parameters. If you put a lower flow into your ion source from your LC, your source parameters will be less. So here, the way to read this chart is to talk about the LC flow first, so to choose which LC flow you're working with, and that depends primarily, I guess, on your column and also a little bit on your experiment, but primarily on your column. And then these are the settings that are the best for the gas 1 and gas 2 and temperature and so on. We didn't talk about curtain gas yet. That's technically part of the interface, so we'll get to that in the next section. And like I said, the probe position, especially at the beginning, I would just leave it in the middle and not touch it, not play with it at the beginning. Personally, I rarely ever touch the probe position. So those are the typical flows based upon the LC flow. Just put a star here in your notes because this is one place where you can actually do some damage to the instrument if you don't set it up correctly. Pretty much everything else is foolproof, but here there is really no way for us to tell what LC flow is going into the ion source. And if you, for example, put too much LC flow into the ion source for your settings, you can cause a flood in the ion source. So let's say, for example, you are using 800 microliters per minute. That would be based, on a slightly larger LC column. And then you use the temperature and the gas settings for lower flow, right? That's not enough gas and not enough temperature to evaporate 800 microliters per minute. And so that liquid will start to build up in the source. And that can affect the vacuum, it can affect the dirtiness, and it can cause a flood. So this is an important thing to think about. And like I said, when I set up the methods for you, I guess that'll be tomorrow, we'll go over this again, and I will set up methods for you that work. And then I suggest you to, especially at the beginning, to not do a lot of method development and use those methods. But this is one thing that people often forget. They change something in the method and they forget to come and change the ion source parameters. The ion source parameters are flow-dependent parameters. They depend on the LC flow. So if you modify your LC flow, for example, you change your column, then you need to think immediately, I need to check my source parameters as well. And you can come back to this chart just to reference what are the correct values. And again, if you are stuck on this, you can send me a quick email and say, this is what I'm doing, is it okay? Especially at the beginning, that's no problem for me. Okay, so how do you choose the correct ion source? In order to speed things up, I didn't talk about APCI in today's lecture. I took that out. Many customers don't use APCI anymore. APCI stands for atmospheric pressure chemical ionization. And you see this slide shows you how to choose the correct ion source, and it also kind of shows you why APCI is not so popular anymore. So here we have a chart, and this chart shows you two parameters about your compound. On the x-axis, we have the polarity of your compound. So high polarity compounds would be peptides and proteins, and low polarity compounds would be something like a steroid, or PAH stands for polyaromatic hydrocarbons. Those are compounds made up only of carbon and hydrogen. They have no nitrogen, oxygen, sulfur, nothing like that. And then on the y-axis here, we have molecular weight. So here's 1,000 Daltons, 10,000 Daltons, 100,000 Daltons. The yellow area is the electrospray area. That is also called by SCIEX turbo ion spray, because we have this turbo V source. However, it's just electrospray. Now, electrospray, the yellow area, continues in the back as well. So electrospray is this huge region. APCI is this striped region. And you see most of the APCI and the electrospray overlaps. So most of the advantages that you get from APCI, you can probably get it from electrospray as well. There's just a very narrow band here where a few steroids might work better by APCI. Now, if you were doing a targeted analysis and you only wanted to analyze those compounds, I would say, sure, change the source to an APCI. In your case, the instrument is not targeted. As we discussed, the instrument creates these very wide open methods that can analyze many things. It's probably not worth it to change APCI. So if you do need to do that in the future, we can come back to it. However, just to keep things simple in the first week, I will not discuss about APCI in the instrument. We can come back to that again. Unfortunately, photospray is not available on the X500R, so we don't have that capacity. Photospray candidate would be polyaromatic hydrocarbons, although there are methods now even to analyze PAH by electrospray as well. So electrospray is kind of moving in this direction here to cover more and more low polarity. But I just wanted to introduce that to you in one slide, in case you hear about these words like APCI and photospray and so on, what exactly is going on there. All right, so we'll skip the APCI stuff. I didn't take that one slide. Okay. Anyway, you have the slides there. You can read them. Okay, so we're on the interface. All right, so we have half an hour, so let's hope we can get through the interface and maybe the quadrupole section today. All right, so the vacuum interface is now the next section of the instrument. So you remember in our flow chart that we had at the very beginning of the lecture, the interface is the region that brings us into the vacuum chamber. So it's the connection between the ion source and the mass analyzer. It's perhaps the most troublesome region of the instrument. It's definitely the part of the instrument which you need to clean it. Our interface is quite simple. We have these different plates. Excuse me, hang on a second. Sorry. Excuse me. So you have these different plates. There are two plates. One is called a curtain plate. And actually, if you look through the source window, you can see that. It just looks like a silver disc. And it has a little hole in the center, and that's called the curtain gas hole. And then behind it, you can't see it when the instrument is in normal operation. You have another plate, and that is called the orifice plate. And you have another hole in that orifice plate, and that's called the orifice. So you just have these two plates with these two sequential holes. On this side, you see we are on the side of the source. This is atmospheric pressure. And here we have Q-jet, Q0, and then quadrupole. This is inside the vacuum of the instrument. So one side has atmospheric pressure, and the other side has the vacuum. Now, why do we have two holes, right? Two plates. And the reason is that we have this curtain gas. And the curtain gas is pumped at a little bit of positive pressure in the empty space between the two plates. And the curtain gas is extremely pure nitrogen. This is why you have the nitrogen generator. The nitrogen generator is generating the curtain gas. And this very, very, very clean nitrogen is pumped out of the orifice at a slightly higher pressure. So you see that the flow of the nitrogen gas is in the direction of the arrow. So the nitrogen gas is coming out. All right, so you may think, okay, how are the ions getting into the instrument, right? Because it's a vacuum, right? Like your vacuum cleaner in your house, right? When you go around with the vacuum cleaner, it sucks everything inside. Isn't the instrument sucking with the vacuum everything into it? Well, think about that for a second. If we did that, we would basically end up sucking the whole contents of the lab into the instrument, right? All the atmosphere in the room and everything, all small hairs and dust. I mean, that would be a huge mess. The instrument would get dirty very quickly. So what we do is we have the vacuum here, but it's balanced by this flow of very clean curtain gas out of the orifice. And the curtain gas then pushes away all the neutrals, all the dirt, all the particles, all the dust, and it keeps this region in front of the orifice very, very, very clean. And we manipulate the ions. You see the ions are this kind of light green color. We manipulate the ions into the instrument with electrical fields. So here at the source, we talked about this already, we have thousands of volts. At the detector, way back here at the end of the instrument, we have thousands of volts, the opposite polarity. So that polarity difference is pulling the ions through the curtain gas and into the instrument. So it is not the vacuum that is sucking the ions in. If we did that, we'd have a mess. The vacuum is there because we need it in the quadrupole region, but the vacuum is balanced by this flow of curtain gas, and the ions are drawn into the instrument by an electrical field. And that also helps because anything that doesn't feel that electrical field will just go straight down. So anything negative, for example, if we're working in the positive mode, and any, like I said, dust or whatever will just be blown away by this curtain gas, it'll go down. And if you remember from the diagram, the source exhaust is here. So the source exhaust is evacuating all of this out of the source. So what do you have that you can control here? Well, you can control the flow of this curtain gas. And if you go back to that chart, where is the chart? So if you go back to the chart, you see it here, right? And I mentioned at the time, this is actually technically part of the interface, although you see it listed with the source parameters. Typical values are around 35, and it's PSI, which is pounds per square inch, around 35 for working with medium to high flow rate. Only at very low flow rate can you turn it down to 30. The curtain gas is your safety. The curtain gas is keeping your instrument clean. So the rule is you really want to use the highest curtain gas that you can in order to keep this region as clean as possible. So that's how the interface is working. It's a very elegant solution, but it does build up dirt on the sides of these plates, especially around the hole. And once dirt is accumulated there, the electrical field is not as nice, not as equal, not as smooth anymore, and so you will not have as good ion transmission. So we do need to take this apart and clean it, and you also can clean the Q-jet and also the Q0. The first times you do that, I recommend you have the local service to help you and to watch and to perhaps participate that under the direction, and then after a couple times you will gain the confidence how to clean it yourself. So here we have some real pictures. So this is what the orifice plate looks like. So this little hole right here in the orifice plate, if I go back to the slide, that is that little hole right there. So that's the entrance. The ions go through that. This is the back side of it. And then here's a picture of the Q-jet. So this is an ion guide. This Q-jet, this part of the Q-jet sits right here behind the orifice and just takes the ions through it like this, and then to the Q0 and then to the Q1 and so on. And here's another, let's say, diagram of the Q-jet, and this will also get some dirt up around here at the entrance to the Q-jet. This part of the Q-jet here is this part of it here, and this part of it sits here behind the orifice. Now this lens is removed here. This is what we call a lens, and this usually sits right here at the back of the Q-jet. And you see there's a little hole in it, and this will have a voltage applied to it. So just like a lens, in your glasses, for example, if you're wearing glasses, that lens in your glasses focuses the light onto your eye, to your retina and so on, so that you can see clear images. We have the same kind of concept with an ion lens, except an ion lens is a hole in a metal plate, and we put a voltage on it. And the voltage that we put on that lens controls the ions going through the hole. And by changing the voltage, we can focus. So you can imagine if that plate, here it is in green at the back, this kind of, not very nice green color at the back. That's the lens, and it's called the IQ0 interquad 0. When it's dirty, then you will start to see poor sensitivity for the smaller ions, less than 200 mass. And so then it's also time to clean. And this whole thing slides out of the instrument, and you can take it apart, just like in this picture, and you can sonicate it, again, in very clean solvent. Probably you want to use LCMS grade solvent for this as well, and clean it and put it back together, and then you'll be able to gain your sensitivity back. So that's the analyzer, that's the interface region. Now we'll go to the analyzer region. So maybe we can discuss the next 20 minutes the quadrupoles, and then we'll talk about the details of the TOF when we start tomorrow morning. So I'll just ask, are there any questions at this point?
Thank you, Alek. Actually, we have a question concerning the samples preparation for tomorrow.
Okay.
So we'll have the group from the research group of Dr. Saliba working first their samples. So we'll have Rachel and as well as Amira. They're here with us today. They can tell us a little bit about their samples, but we want to ask when we want to spike the sample with the triazine, is there a specific concentration that we need to add?
Yeah, I mean, you can add something like maybe, let's see, 20, so the final concentration is like 20 ppb. So I think the idea would be when you spike, you don't want to add a large volume.
Correct, yes.
Because the large volume will change the composition of the sample. So I don't know, what's your sample volume?
So Rachel,
that was a question, sorry.
Yeah.
Your sample volume?
So Rachel, can you let us know about your sample as well?
So hi Alek. So I just want to introduce a little bit our samples. So our samples are polychlorinated biphenyls in biological samples. So people in the literature are working with these compounds in gas chromatography since they are non-polar compounds. So we wanted to ask if these compounds could be analyzed on HPLC QTOF.
Yes. Didn't we try that in the demo? Because I did a demo for you guys, right? Didn't we try this in the demo and it didn't work, right?
I wasn't with you. I don't think I was.
You remember? Was somebody there? Because I remember there was like 3
can you let us
sets
know
of samples.
where they tried already?
Sorry?
I'm asking Grania, were these tried already? Or Juan can also help us here.
I think prior to acquiring the instrument, we did some tests at the factory, but I don't know if we are talking about the same compounds.
Oh yes. Labis was using these samples. Yes.
This is not the compounds to start with. I think if it didn't work in the demo, it's not going to work now.
Yeah, in the demo, we had the three groups of samples, so I don't recall exactly which ones that weren't that we weren't able to detect the compounds in them.
I don't know if you can see my screen, but I'm looking in my archives.
Yes, we can see.
I save everything. So at that time, this is Dr. Saliba. This is what we are talking about.
Correct. Yes.
Yes.
Okay, so this was plant extract. Learn how they work first, and in this case, actually, the quadrupoles are just passing everything, so they are not actually even used as a mass filter. We call this it's abbreviated RF, or radio frequency only mode, and here the ions really pass everything. Nothing is filtered, nothing is blocked, and then the time of flight measures the parents. Now in MSMS, we use the quadrupoles as a mass filter. Here in Q1, you can see we are selecting one particular mass. That's the parent. It enters into the Q2 in the collision cell, fragments into pieces, and then the time of flight does the accurate mass measurement of the pieces. So we have these two modes. You can see how we use the quadrupoles. In one mode, the MS mode, you can think of the quadrupole as not being used. However, it is still working to transfer all the ions. Here we are actually using the quadrupole as a mass filter to select just one mass. So how does that work, and how do we use the quadrupoles in these different ways? So the function of a quadrupole is three modes. So we have the transfer ion mode, and as I said, that's used in TOF-MS. Transfer means everything that's at the front of the quadrupole will be transferred through to the back of the quadrupole. There is no mass filtration. And then we have the select ions with a specific mass per charge value. And that is what we do in MSMS. So we are selecting either one mass or a range of masses, and we are sending only those to the collision cell. Everything else is blocked or lost. There is a third way that we use the quadrupole, and that is called scanning. However, it's not really used in QTOF. The reason for that is scanning a quadrupole is very slow. So we typically only use that in a different kind of instrument called a triple quadrupole. But we can scan the quadrupole, and that means sequentially sort the ions by their mass per charge value over a range. Let's say, a scan from 100 to 1,000. In a QTOF instrument, we have the time of flight, and the time of flight does the scanning for us. And the time of flight is much faster, and as we already learned, has better resolution and better mass accuracy and all these things. So for that reason, we rarely use the scan of the quadrupole in a QTOF instrument. So how does the quadrupole work? Let me show you actually the diagram first. So here's a diagram. This is a picture of a quadrupole. And you see the quadrupole is 4 parallel rods. So here, 2 of them are marked blue and 2 of them are marked red. And these are very accurately machined parallel rods. Now they have a radio frequency applied to them. Radio frequency, so this is an alternating current. And the ions pass in this empty space between the rods, and they make like a corkscrew motion in resonance with the radio frequency. And by controlling that radio frequency, we can control which ions pass. We can either allow all of them to pass, or we can specifically allow one mass to pass. And that's how we get either the transfer or the select modes by controlling that radio frequency. So we have a set of 4 parallel rods. In this case, 2 are blue and 2 are red, but they are machined exactly correct. The blue and the red just means the polarity that is applied to them, the electrical polarity. And that electrical polarity is changed with a radio frequency, causing the ions to move through the empty space between the rods. So I'll share this. Now it's an animation, so I hope the internet is fast enough to transmit it to you. So here we're looking at the quadrupole rods on the axis. So the gray circles represents the cross section of the rods. So these are the 2 rods that are positive and these 2 are negative. So just to show you again, we go back to that 3D diagram, right? That's a cross section of these 2 and these 2 rods. So a cross section taken right through the rods there is that. So we're looking at it on the end. And you can see that we have 1 positive ion. So if we look at the force field that ion feels, it will be repelled by the positive rods and it will be attracted to the negative rods, right? This is the basic principle of electricity. Charges attracting and repelling each other. And so then the ion will cause to move in the direction of the red arrow. And what happens is just as it moves, now the polarity of the rods has changed as the polarity is changing with the radio frequency. So now we have a different force diagram and the ion is in a different position. So the force changes and it pushes again the ion around in that little quarter circle. And this keeps going, and so the ion makes this circular path, which actually is a corkscrew through the rods. So here's the animation. I hope it will work nicely for you in the internet. So you see the changing of the rods, and the ion is making that circular pattern. Now, if we look at it, so some German language, but if we look at it from the end point, 3-dimensionally, you see the corkscrew motion that the ion is making as it passes down the rods. So that's how the quadrupoles work as a mass filter. Very different than a time of flight. These are very, very different types of analyzers. And that's really what's so cool about this instrument is that we're putting these 2 analyzers together and we're using the best features of both of the analyzers.